Hello and welcome. In this video, we're going to get into some of the basics of continuous random variables. So recall that the probability distribution for the rolling of a fair six-sided die is as listed in this table. So we have 6 possible outcomes. We can roll a 1, a 2, a 3, 4, 5, or 6. And each of those occurs with equal likelihood, 1/6. So we could generate a frequency distribution or a histogram that shows the frequency of each of these 7 outcomes. So there's out of these 6, we see that 1 appears 1 time, and then moreover, rather than doing frequency, we could say that this is relative frequency, and we can say that each of these has a height of 1/6. So what we would say about these outcomes is that they are uniformly distributed outcomes. And by uniformly, we just mean they're all the same, that they all follow the same likelihood. But this is great. However, what about situations where it's possible to actually have an outcome somewhere between 1 and 2? So maybe we're generating a random number, and that random number could be anywhere between 1 and 2. So it doesn't suffice any longer to think about this as a discrete situation. So some variables are continuous. For example, if we were to consider the distribution of say, daily revenue of an online marketplace, we're going to find that there are infinitely many possible revenues to be made, especially as you begin rounding to the nearest cent and maybe to the nearest thousandth of a cent. There are many outcomes, and so you get effectively a distribution that now has continuous outcomes. In other words, instead of saying on a number line, for example, that between 0 and 1, that we only have the outcomes 0 and 1, imagine that not only could we have those on the number line, but we could also have anything in between. And this is continuous because there are really infinitely many choices between 0 and 1, versus in another situation where the only 2 possibilities are, say, 0, 1, and maybe even 1/2. We say that this is discrete because the number of values is finite. In other words, not infinite. So while it's great to work with discrete distributions in situations where your random variable could take on one of a finite number of values, it also is important to be able to consider continuous distributions, because a lot of variables are continuous, like the height of a person, the weight of a person, or the weight of an object. Those are all continuous random variables. In a simple setting, suppose we tell our computer to generate a random number between 0 and 1. Every value between 0 and 1 has an equal likelihood of being selected, and there are infinitely many values. This is what we call a continuous uniform probability distribution. Up here, with the die rolling example, we have a discrete uniform probability distribution. And so what's this going to look like? Well, in this case, if we're generating a random variable and we want to look at the say, density, or we could even say maybe relative frequency. The density is usually a term used when you're dealing with continuous distributions, because the relative frequency of any one outcome is actually 0. Well, wait a minute. Let's think about this for a second. Okay, so if 0 is the lowest value and 1 is the highest value, then if I want to ask, well, what's the probability that I draw a random number and it's exactly equal to 0? Well, because there are infinitely many values between 0 and 1, each of which have an equally likely outcome, well, that means that if there are infinitely many values, they would each have a probability of effectively 1 over infinity, which is 0. So think about it this way: what's the likelihood that you find somebody who weighs exactly 150 pounds? Well, maybe 150.2 or 149.8. but the likelihood that you find somebody who's exactly a certain weight, and of course our measurement devices come into play here. It's not possible to measure someone to perhaps a great amount of precision, but still the probability of getting somebody exactly 150 pounds is very, very unlikely. So what we're going to do is I'm going to draw a horizontal line here. And this horizontal line is going to represent the fact that between 0 and 1, every outcome is equally likely. Now, one of the things that we like to do is we like to let the area under this curve, or the area under this line, we want this area to be 1, okay? We want this area right here to be 1. Why is that true? Well, if we think about the density as if I find the area between a certain range, for example, the area over the interval from 0, beginning at 0 and ending at 1, is 1, which is 1.00, which is 100%. So the area under this represents the probability of those outcomes. So if you're generating numbers between 0 and 1 uniformly, meaning that every number has an equally likely chance of coming up, then there's a 100% chance that you generate something between 0 and 1 because your random number generator is set to do that. But what this also enables me to do is, for example, to find the area between two other points, like the area over, we'll say, the interval from 1/2 to 1. Well, you can probably think about this intuitively enough to say, well, that's from 1/2 to 1, that's going to be half of the area, and so the other half of the area would be from 0 to 1/2, and since this is a rectangular shape, that means that the area, if you were to slice this thing in half, is 0.5, which is 50%. So there's a 50% chance that you generate a number that falls between 1/2 and 1. And even though there's a 0% chance that you pick any specific number, like 0.5349, there is a 50% chance that the number that you generate falls in an interval. So the key here is we're going to be dealing with intervals instead of generating a specific value and finding the probability of that kind of outcome. That makes sense in discrete situations where the number of outcomes you have is finite, but it doesn't make sense in situations where the number of outcomes you have is infinite. Okay, and you could also intuit from this that if I were to say, well, what's the area between 3/4 and 1? You could probably tell me pretty quickly, well, from 3/4 to 1, that represents a quarter of the entire area of this rectangle, and so you could probably tell me that the area there is 0.25, or the 25% chance. So the probability that your random number generator gets something between 3/4 and 1 is 25%. One last thing, it doesn't really matter whether we use open intervals or closed intervals. So for example, if you say, well, what if you exclude 3/4? Well, we've already mentioned that the probability that x is some particular value is 0%. Because there are infinitely many values, so the probability that you get any one specific value is 1 over infinity, or essentially 0. And so whether you include 3/4 or not in that entire interval, well, 3/4 is just a point value, and it has a 0% chance of coming down. So whether you include this point or not is not going to affect the probability. We'll just use closed intervals for the sake of consistency. All right, in general, let's say that we have a uniform distribution for a random variable x over the interval from a to b. Now here a was equal to 0 and b was equal to 1, but you can probably agree that it just depends on the context. What if I were generating a random number between 7 and 14? Well, then my a would be 7 and my b would be 14, and my rectangle would be between x equals 7 and x equals 14. So this is a general way of doing that, and we'll take a look at a couple of examples in our next video. We write that x is distributed, this little tilde means x is distributed, the u stands for uniformly, over the interval from a to b. So x is distributed uniformly over the interval from x equals a to x equals b. This is a nice compact way of saying that. Now the equation of this function, because we're going to need to be able to find areas underneath it, this function is actually 1 over b minus a. So up here, f of x is equal to 1 over 1 minus 0, which is equal to 1 over 1, which is equal to 1. So that means that this function, this horizontal line, is the line y equals 1. And that should make sense because if you think about, well, this is actually a square. It's 1 unit wide and 1 unit tall, but we haven't drawn it proportional to size. So 1 times 1, the area of this entire box is 1. The area in that box is 1. So if you think about why we do this, why it looks like this, and also we'll state that the average value is basically the average of the beginning of that interval and the end of that interval. And the standard deviation looks kind of funky. It's the difference from b minus a squared divided by 12. And we'll talk about where this stuff comes from. Now a little bit of intuition though. If I say that here I have this interval from a to b, and then here's my rectangle, and I want to know what this horizontal line is that models the top of that rectangle, then what I do know is that this distance right here, that is equal to b minus a. It is b minus a units wide. And then what I'm trying to solve for is how tall this is right here. And let's just go ahead and refer to that as h. Okay, in our context, f of x is actually the height, and we know that if we take the height and multiply it by the width, height times width, this area right here is equal to 1. So we need that to equal 1, and we want to figure out what the height should be, so we divide both sides by b minus a, and hey, there's our function. Height equals b minus a. We'll call this f of x. It just happens to be that the height is the same all the way across, and we've got our probability density function. That's the intuition. Now we can also do this with integrals. We can say that the area starting at a and ending at b, from x equals a to x equals b, of this function should equal 1. I'll say with respect to x should equal 1. Now, one thing I know about this function is once again, it's going to have a constant height. So let h represent its constant height. The antiderivative of a constant, in other words, what function do I have to take the derivative of in order to get a constant? Well, that will be h times x. In other words, what function has a constant slope? It's going to be a linear function. And we know that this is going to be evaluated from x equals a to x equals b, and it should equal 1. So our unknown right now is h. So if I plug in and evaluate this at x equals b, minus evaluate this at x equals a, actually I can do this one better and say h times b minus h times a equals 1. Now I want to solve for h so I can factor that out. And you can see once again that we get h is equal to 1 over b minus a. Clearly the intuitive route is a lot nicer. Now if I were to ask you what's the average value between these, you could probably tell me pretty quickly that it's going to be right in the center of this, that's going to be the average value because it separates it finds the balance point between all of these values from here to here and all of these values from here to there. But we can also do it by definition. We can say that if we look at the sum of the from a to b of the function of x times the function, the value times the density, dx, our density function is 1 over b minus a. So I'm actually going to, this right here is going to be 1 over b minus a. That's our probability density function. And then it's going to be times the integral from a to b of x dx. Okay, so this is going to give us 1 over b minus a times 1/2 x squared. It's the antiderivative of x. You take the derivative of 1/2 x squared, you'll get x. And we're going to evaluate this from x equals a to x equals b. Okay, well if we do that, we're going to get 1 over b minus a, and all we're doing here is just showing you the derivation of where this comes from. 1/2 b squared minus 1/2 a squared. Now, I'm going to go ahead and factor out a 1/2, and also b squared minus a squared. This is a little factoring note. This is the difference of squares, and that will be b plus a times b minus a. So if I factor out a 1/2 from this, I'll have 1/2 times 1 over b minus a, and then b plus a times b minus a in parentheses, and I see that these two cancel right there, and I get 1/2 of b plus a, which is the same thing as writing b plus a over 2, or better yet, a plus b over 2. So again, we were able to do the expected value intuitively. This is just the integral calculation of how we would compute the expected value. We would do a similar thing for the standard deviation, but I don't think that's entirely necessary at this point. In the next video, we'll go ahead and take a look at a couple of examples of working with these three pieces.